So today we're going to be talking about some specific exponential models for growth and decay. So for growth functions, there's a set formula we can use given an application problem related to exponential growth. And that formula is y equals c 1 plus r to some time period. And so c is our initial amount, or sometimes called the principal. Initial amount. And t is our time, so time in years or months or however it's defined. And then here's our rate. Now, what's important as we look at these growth and decay functions is that we always put rate in as a decimal. Okay, so we have rate as a decimal. And I'll just look at growth and then we'll look at decay afterwards. So if I'm given an application problem, like what I have here, so I have $500 that I'm going to put into an account that pays 8% annual interest, annual meaning yearly. What's the account balance after 6 years? So first thing I want to do is write an equation that models this situation. So I have y equals $500 is my principal or initial amount. And then I have 1 plus my rate. Now my rate is 8%. 8% as a decimal would be 0.08. So I'm adding in 0.08. Okay, 1 plus 0.08. And then to some time period. And I can clean that up. So here's my function. If I add the 1 in the 0.08, I have 1.08 for my base value here. And we learned on our last set of notes when we were talking about graphing, if it's a value greater than 1, then it's growth. And if it's a value less than 1, then it's decay. So we can see here that I have a value greater than 1. This is going to be exponential growth. Now we want to know, well, if we let that money sit for 6 years, so that's saying a time of 6 years, what would my account balance be? So I have 500, 1.08 to the 6th power, because I'm now plugging in 6 for time, and I'm just going to use my calculator. And 500 times 1.08 to the 6th power gives me 793. Now we're talking about money, so I'm going to round to 2 decimal places because that would make sense for money. And we would have $793 and rounding 44 cents approximately. Okay, so using our formula to put the parts together to create a function that then I can put in a value for time. I can also put in, I could have said, after how many years will the account be worth $1,000 or something like that. And that we'll talk about further on in the notes. That's a little more complicated when it gives us the output versus the input. Okay, when it gives us a y value versus t value. Now let's look at the graph real quick, just so we can kind of link this back to what we were doing before. So here was our function, 500, 1.08 to some time period. Now we know that this is growth, okay, that it's going to look like this, just going back to how we graphed on the notes before. We know that the horizontal asymptote is at 0. And our anchor point, the only transformation I have here is this 500 out front. So 0, 100 becomes 0, 500. I have no left, right shift and no up, down shift. So just doing a quick sketch of that. So I'm going to have my scale on my y-axis go by 100, 300. And I'm going to go up to like at least 1,000 here. 100, 900, 1,000. Okay, that's good. And then I'm going to go time in years. So 1, I'm just going to skip every other so it's not too crowded. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so here's time in years. And here is our account balance and money. And using what we know about graphing, and we know our anchor point is at 0, 500, which also makes sense then in 0 years, I just deposit that $500. There's no growth on it yet. So at that point. Now, before we just draw that in, and yes, we're not going below 0, horizontal asymptote is 0 there. I'm actually going to use our info from here to just get a little bit more of an accurate graph here. So I know that in 6 years, let me zoom this out a little bit, I'll be at $793. So 6 years, 793, so almost at $800. So it's not going to shoot right up, right? It's a slow growth rate. It's only 8%, which actually is a huge growth rate in terms of what a bank would actually give you, would be much less than that. But still, it's not super rapid. It's 8%. So it's slow growth. We won't even see this half of the graph, so we won't really approach the horizontal asymptote. We'll just kind of start at 0 and continue. And that's probably too much of a curve even really what I should be giving it. Okay, and it'll grow over time. The account will grow over time. So that's our exponential growth. Now, the only difference between our exponential growth function and our exponential decay function is that with decay, we're losing value exponentially over time, right? And so it's our same formula, but instead of adding our rate, we're subtracting at a certain rate from 100%. So the 1 is 100%. So I have 100% of something plus I'm growing at this rate, or I have 100% of something and it's decaying or I'm losing at this particular rate. Okay, so the only difference from growth and decay in these formulas is the plus or the minus in the middle. Okay, same values all mean the same thing. So initial amount, rate, which has to be a decimal, and time. Now, a great example of exponential decay is purchasing a car. So you buy a car, used car for $18,000. The value of the car will be less each year because of depreciation. So this is a good word to know. Depreciation means losing value. So many times in exponential decay word problems, they say it depreciates at that rate. So in the next sentence, you see that depreciates, loses value. So that's a vocabulary word you need to know. The car depreciates at a rate of 12% per year. What will the value of your car be in 8 years? So first, just like we did over here, let's write just our general function here. So the car value, the initial amount is $18,000. We are going to subtract from 100 our rate, or subtract from 1 our rate. So 12%, remember we have to put in as a decimal. So I put it in as 0.12 to some time period. Now I always like to really clean up the decay problems before getting started. So 1 subtract 0.12 is going to give me 0.88 to our exponent of t. So again, less than 1, between 0 and 1, this is a decay function. Okay, so I can see that kind of relationship to stuff we've already talked about. Now we want to know after 8 years. So time is 8 years. So I started with a car that was 18,000, depreciating at 12%. So depreciating at 12% means each year I'm maintaining 88% of the value of the year before. Okay, so you can kind of think about it both ways. And we want to know in 8 years, where will we be at? And so at my calculator, 18,000 times 0.88 to the 8th power. And after owning that car for 8 years, now it's worth about 6,473. And again, it's money. So I'll go to 2 decimal places and 42 cents. Okay. So in 8 years, if you were to try to sell it, you're probably only going to get like $6,000 for that same vehicle. Okay. That's just how it works when you buy a car. Now, in terms of graphing, so let me rewrite our function here. So we had 18,000 and 0.88, some time period. So now instead of a fraction, right, when we were doing growth and decay functions, we either had like 2, 3, we had some value that was greater than 1, or we had a fraction. Well, instead of a fraction, now we have these decimals that are less than 1. Okay, showing us that this graph is going to be decay. It still will have a horizontal asymptote at 0. And the anchor point, 0, 1, would become 0, 18,000. Okay, with this value out front, and then no left, right shift, no up, down shift. So on this graph, I'll go by thousands. So 1,000, 2,000, and then to save for space, I'm going to start skipping. So 3, 4,000, 5, 6,000, 7, 8,000. I think it will fit 9, 10,000, 11, 12,000, 14,000, 15, 16,000, 17, 18,000. Okay, so there on my y-axis, I have the car value in money. It's our units. And then on our x-axis, we'll have years. Oops, sorry, it should be time in years. So I'm about to write it opposite. So we have time in years. I'm going to skip 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We know that our anchor point has gone from 0, 1 all the way up to 0, 18,000. There's my initial amount. And that it's decaying, that my graph will look like this. We do know one other point, which will help us get a little bit more of an accurate picture of our graph. So the other point we know is that after 8 years, it'll be $6,473. So after 8 years, here's my 6,000. I'm somewhere between 6,000 and 7,000. So maybe I'm just here, just to kind of give me another point. So again, it's not going to be like steep decay here. It's 12%. Draw in as best I can. Okay, and obviously with these models, most likely the car is never going to be worth like 0, right? It's going to approach 0, get really, really close to 0 and not actually touch it. But at some point it's going to actually probably plateau before that. Like you can sell it for $1,000 or whatever, even if it's 30, 50 years old. So it's going to follow this model for some amount of time. And then eventually it may plateau and not necessarily continue to follow that decay at some point. It may become more like a plateau, just because a car usually keeps some value at some point. It doesn't continue losing at that same rate possibly. Okay, so let's look at a few examples of how this will look when we're doing some application problems. So first thing we want to do is always be able to write the exponential model for whatever situation it gives us. So here we have population. Population could increase or decrease. This is an increasing population, increasing at a rate of 4% each year. Here's my initial amount, and here's my rate. And remember, I have to put in my rate as a decimal. 4% is 0.04. We know that it's increasing, so it should be growth. So I have my initial amount, and then because it's growth, I'm adding in my rate of 4% of 0.04. I'm just going to clean that up. Instead of 1 plus 0.04, I'm going to write it as 1.04 to some time period in years. And it just says determine the population after 8 years. So first I need to be able to take the sentence and make my exponential growth function, okay? Then I'm going to use this to determine something using my model. So 8 years means I'm just going to plug in 8 for t. I'm going to use a calculator to do that. So 54,000, going at a rate at 1.04 to the 8th power, that in 8 years, and we're going to approximate here. So we're people, so I'm just going to go to the nearest whole number. So approximately 73,903 people. Okay, rounding to the nearest whole person. Our next example is Brenda, who drank a cup of coffee. This is another really common one. So like some sort of, either you take some medicine or drink coffee and you have a certain substance that's in your system. When you initially drink it, you have a certain amount of that substance in your system. And then over time, that amount diminishes, okay, depreciates over time. If I take a Tylenol at 500 milligrams, in 3 hours, it will be less than 500 milligrams that's left in my system. So we can write a function that models this, kind of how that works when you put a substance in and it's slowly diminishing from your body. So she drank a cup of coffee. That cup had 135 milligrams of caffeine. For each hour after you drink caffeine, your body, it says here, is diminishing at about 15%. Okay, diminishes, losing some of that caffeine content in your system. So that's going to be decay. I know that I'm starting with 135 milligrams of caffeine. That's my initial amount. I am losing milligrams of caffeine by 15% in each hour. So minus 0.15, again, as a decimal to some time value. Now for this, our time is not in years. So it's telling me that this depreciation, that this diminishing effect is by the hour, not by the year. So this time is going to be number of hours. And I'm just going to clean this up a little bit. So I'm going to have 135. If I take 1 and I subtract 0.15, that leaves me with 0.85 to some time period. And there's my function. Decay less than 1. And then we want to know 4 hours later how much caffeine would remain in her system. So 0.85, 4 hours later, 135 times 0.85 to the 4th power, and about, and let's just go to, oops, I didn't type that in right, hold on. I typed in 125 instead of 135. 135 to the 0.85 to the 4th. Okay, so let's go, I don't know, we'll do the tens place. So 70.5 milligrams about of caffeine would be left in her system after 4 hours. Okay, so those are some really straightforward application problems. Other things we want to be able to do is understand what a function is telling us. So if I'm given a function, I should be able to determine if it's growth or decay, which I know that this is growth because it's greater than 1. What is the initial amount and what's the rate that it's growing at? So my initial amount, remember, is this C value that's out front. So my initial amount for this function would be 20. Now to find my rate, I need to remember that here's my general exponential growth function, right? And so this piece right here was equal to 1.23. So I took 1 and added some rate and it gave me 1.23, or my rate must be 0.23. I'm just subtracting 1 from both sides. Now I'm not going to write my rate as a decimal. I'm going to say, okay, my initial amount was 20. I have exponential growth and it's growing at a rate of 23%. Okay, this 0.23 means it's growing at a rate of 23%. On our next example, because this is a value less than 1, I know that this is exponential decay. Again, this amount out front's my initial amount. And so here's my exponential decay, right? I have 1 minus a rate to some time period. And so I know that 1 minus a rate equals 0.64. So this one, if I were to like do actual solving of an equation here, I'd subtract 1. So I'd have 0.64 subtract 1, giving me negative, let me go over here, negative R equals negative 0.36, or R equals 0.36. Okay, if I'm left with, and another way to think about this is it has to add up to 100%, right? So if I'm decaying and I have 64% that I'm maintaining after each time period, well, I have to add up to 100 with my rate that I'm decaying at. So 64 plus 36 gives me 100. So there's a kind of a few other ways to think about this. I don't feel like when I look at these, I actually want to go through and do this. I go, okay, 64% remains. So that means I'm decreasing at 36%, and I'm just adding up to 100 in my head. That's what I would kind of suggest you do to give you a kind of understanding why that works, is because we're always taking our rate, subtract 1, and that 1 is 100% as a decimal. 100% as a decimal is 1. Okay, so that gives us, and again, our rate should be a percentage. So a rate of 0.36 means we have 36% that we're decaying at. Now, sometimes our growth and decay is given to us as a fraction, so we have to be careful. This is a fraction, but it's still exponential growth. It is growth because 7/5 is the same as 1 2/5. Okay, it's an improper fraction. It's greater than 1. So I know that it's growth. My initial amount is 10. Now 1 2/5 I could write as 1.4. So if I know that I have growth and it's 1.4 is what my is inside my parentheses here, then that tells me that I'm growing. So there's the 100%, and I'm growing at a rate of 0.4, or 0.4 is 40% for a growth rate. Okay, so sometimes with our fractions, we really need to think about, is it growth or decay? And then we need to think about what is that fraction as a decimal, so I can look at the rate as a decimal to write it as a percentage. Okay, one last thing I'd like to do today, and that is going to be some calculator work with these. So we've already done a couple of application problems, so I think you can get started on this one, but you won't be able to finish it with what we've done so far. So what I'd like for you to do is go ahead and do the first 3 parts of this question, and then wait to do the last part. So do all 3 parts, then play the video, see how we compare, and then we'll do the last part together. Okay, so first of all, don't ever miss this piece. I feel like students lose points a lot for not writing the general model. So here's my general model for the situation. So I have $5,000 initial amount, growth of 24%, amazing growth rate. And then we have time for our exponent. So after 5 years, plugging in 5 for t, that stock would be worth approximately $14,658.13, and you would have had to plug this into your calculator. And after 25 years, we're over $1 million, okay? So that's what we've done with these so far. Now it gets trickier if it asks you to find, if it gives you a y value and it asks you to find the exponent, the time period. So it says how many years before the stock is over 40,000. Now, if I look at my function, my input is time and my output is the money or the account balance. So $40,000 is a y value. And then I have my function, right? 1.24, some time period. So if I just plug that 40,000 in for y, 5,000, 1.24. The issue is it gives me this exponential equation, but I can't do base matching to solve, right? And when we go back to notes 1, when my variable's in the exponent, I can't solve this just using inverse operations. The only tool we have is base matching. That's not going to work here. But what we can do is we can look at our graph, and there'll be some sort of growth of $5,000 growing at 24%. So if this is 5,000 growing up, and then I have 40,000 up here. And what I can do is in my calculator, if I put a horizontal line where 40,000 is, it will hit my growth graph, okay? And I'll be able to figure out what the intersection point and what this t value is, after how many years is my function at 40,000. Now what this really is a system of equations. Here's one equation. It happens to be a horizontal line where y equals 40,000. That's this line right here. And here's my other equation. And I want to know, when are they at the same point? When do they intersect? The system of equations. And our calculator will do that for us because, like I said, we can't do this algebraically right now with the tools we have. So we got to use our calculator. So in my calculator, and clear out what I have here, I'm going to put my function in first. So 5,000, 1.24 the x. Okay, there's my function. And I want to look at when will it be 40,000. That's my other equation. So here's y1, here's y2. Now, if I just go to my regular viewing window, I'm not going to be able to see this. So I'm going to go into window and change my values around, and in particular, my y values. So I know I'm starting at 5,000. So I'll just put a minimum of 5,000. And I want to know when it's 40,000. So why don't we go up to 50,000? Now, right now it has, for me, my x values go from -10 to 50. I think that'll be fine. I know that it will be fine, but I could also adjust this too. I could make this less, more, whatever. Okay, so x min and max is going to tell you what your x values are going to, what your y values are going to. So then from window, I just hit graph, and it'll already be set to show me how I just set it. So there's my first graph. And then there's 40,000. Okay, so here's our function. And then here's our second line, which is at 40,000. In my calculator, if we go second calc, where we were last unit as well, when we were doing 0, minimum, and maximum, if I go second calc, I can also calculate the intersection point. Where do these two lines meet? So if I hit 5 for intersection point, and then remember it asks you questions. We did this during the systems unit. So it says first curve, and it's showing it to me up there. And I go, yep, that's my first line. Second line, and it's showing it to me up there. And I go, yep, that's my second line. And then it says guess, and I would say yes, please, by hitting enter again. And it gives me my intersection point. So what my account is at 40,000 at about 9.6 years, 9.7 years. Okay, so in my calculator, time would be 9.7 years approximately. So let me go down to the bottom and write those steps down for us real quick. Okay. So in calculator, enter equations into y1 and y2. So first enter your equations that you have. So one will be your function and the other will be the value you want to determine it at. And then adjust your window. Okay, so go to window and adjust the minimum max. And then look at the graph. You should see them crossing. And then I'm going to go to second calc. Option number 5, which is intersection. And then I hit enter, enter, enter. And it should show you your intersection point. Okay. So let's look at another problem where we'll try this again together and you'll have some more practice of this on your own. So this is kind of what we're doing in our calculator. If you need to pause that to write that down, go ahead and do that. So let's look at another example. Now this is going to be decay. So a nurse administers 12 milligram dose of a medication through injection. The drug metabolizes, so leaves your system at a rate of 12% each hour. Write a function to model the situation. So again, don't miss this question. Make sure we write the function. So we're starting with 12 milligrams. We're losing at a rate of 12% each hour. So it's important to note that time is in hours. And just cleaning that up a little bit. So I have 12 milligrams, losing 12%. So I'm at 0.88 to some time period, and time is in hours. So first question, how much of the drug is in the bloodstream after 8 hours? That we're just plugging in, right? 0.88 to the 8th power. To get out of your graph, hit second quit. So I type in 12 times 0.88 to the 8th power. Approximately 4.3, and was it in milligrams? Yeah, milligrams. would remain in your system after 8 hours. Then the next two ask about time. So how many hours have passed when only half of the original dosage is left in the patient's system. So my original dosage is 12 milligrams. I want to know, when is it 6 milligrams? When does Y equal 6 milligrams? Because remember, time is hours, and Y is going to be how much of the medication is left in the system. So I want to know, when is it at 6 milligrams? Here's my function. And if I were to try to plug 6 in, right, because it's an exponential equation, we can't solve that using base matching, so we're going to use our calculator. So in my calculator, I'm going to, in Y1, put my function, 12 times 0.88 x power. And then I want to know, when is it at 6? Now, my window was set for the problem above. That's not going to help me so much. So I'm going to reset my window. First of all, it's decay. So the highest I need my Y value to be is 12. That's the initial amount I'm starting with. And I'm just going to go down to 0. Okay, or actually I'll go down even below that just to be able to see my graph a little bit better. Okay, so my Y scale is going to go from -10 to 12. And I probably don't need X to go up to 50. I'm going to change that to 20 hours of time, and let's see what it looks like. So now I've entered in my function and 6, so I'll have a horizontal line where Y is 6. I look in my graph, I've just in my window, there's that medication leaving my body over time. Here's when it's at 6 milligrams. I go second, calc, option number 5, enter, enter, enter. And it tells me that my function's at 6 milligrams when my time is about 5.4 hours. Okay. And the next question is really similar. It says, well, how long will it be until there's only 1 milligram of that drug remaining in the bloodstream? How long? What's the time period? So here's my function. Now I want to know, when does it equal 1? Well, I can't solve that with base matching. So in my calculator, I'm going to have my function. I'm going to have another equation, horizontal line where we're at 1. Get my graph again. There's my function. Here's 1 milligram. Let's see where they meet up. So second, calc, intersection, enter, enter, enter. And it looks like I have 1 milligram left in the system at about 19.4 hours. 19.4 hours. Okay, and like I said, you'll get more practice with this when you do some of the homework for exponential growth and decay.